Welcome back to Wheeled Mobile Robots. So last class what we have seen lecture 11, we have made it two part. So where we were talking about a dynamic model of mobile robot. That too we have taken a very general what you call land based mobile robot. So we have taken two popular method, one is Newton-Euler, the other one is Lagrangian-Euler. But at the end of the lecture 11 part 2, I said that the next class we will be talking about the same equation of motion what we obtained in these two methods. We will write it in a you call state space form. So what that means? We will write it in a matrix and vector form. So that is what we are going to cover in the lecture 12 in the beginning. Then we will move to a dynamic simulation using MATLAB for a generalized land based mobile robot. That is what going to cover in the lecture 12. So what we are actually trying to cover, so we will be trying to cover equation of motion. Then we would be actually like writing the equation of motion with respect to inertial frame. So what that, so you know like this is what the mobile robot having a B as the point and where you can say this is I as the another point. So this is what you call actually like inertial frame. So now this inertial frame you can actually like write it and whatever we have derived that is actually like derived with respect to what you call body frame. So now first we will write the equation of motion in what you call matrix and vector form which we simply call state space form. Thereafter actually like we will talk about the equation of motion with respect to inertial frame. Once these things done, then we will actually like move to the MATLAB environment and we will try to simulate. So both forward and inverse dynamics at an extent and then we will move or we can actually close this lecture 12 and lecture 13 we will actually like talk about more on wheeled configuration. Okay. So now in that sense we will actually like begin. So this is the you can say model we have shown in the last class where you can actually like say that fx, fy and mz we can actually like do it either Newton-Euler or Lagrange-Euler, but the generalized equation what you have actually like obtained, what I mean to say generalized equation, if your body frame and the what you call the centroid is actually like away or it is not you can say same point, they are distinct, then you can actually like get the dynamic model in this form. So now this is what we are actually like considering and we are writing in a very simple sense where matrix or not in this case it is actually like vector to vector we are writing. So now you can see that what we wanted is actually like something we can actually like integrable. So what that means, so you know the state variable which is eta, right, and eta dot and I can write eta double dot, this is one way, or I can write eta and zeta and zeta dot. Okay. So this I can do it. So in the sense you can see that I can write it either this or this form, but I wanted to have this form. Why? Because I told that the tau I can write as function of, you can write in the sense eta dot and eta double dot, or in the other way around if you write f eta then you can write zeta and zeta dot. So this is what I wanted. So in order to do that what I am trying to do, so here you know like u dot, v dot and r dot are the what you call acceleration, so which is actually like with respect to body frame, whereas uv are actually like your body fixed velocity at instantaneous time and you know like the other things. So now what we are trying to do, we are trying to rewrite that into a other way around where we are putting every coefficient of the acceleration. So what that means, so you can see here there is no v dot, so I am putting that coefficient and similarly the second equation do not have any u dot, so that is also I am putting and the remaining equation I am rearranging in the such a way that so I can write it in terms of coefficient of u dot, v dot and r dot. So this is what the overall idea. Now what I can do, I can actually like segregate this u dot, v dot and r dot and the remaining I can actually like put it in one side and I can rewrite this equation. This is what I wanted. So in the sense what you can write x dot I can write as ax plus you can say bu. So where this all vector. So this is what we call state space form. So this is what I also wanted in this way. So in the sense what I can do, so this I am rewriting in a matrix. You can see like now these are the coefficient related to u dot, v dot and r dot and the remaining I am putting as a simple vector. Okay, and equal to the forces which are actually given. So now what you can actually like see, so this particular matrix hereafter we are going to call inertia matrix. Why? It is actually like purely based on the inertia, but this particular matrix has a speciality. What the speciality? You can see the diagonal value all are positive and you can actually like see that off diagonal is actually like similar of the bottom one, or you can say the other way around. What that means? So it is actually like symmetric matrix. In the sense, if I call this as one of the matrix called D, for example, so this D matrix would be actually like positive, and as well as what you can see, the D matrix is actually like symmetric. So this is what one supposed to know in this particular slide. So now this is what I am going to write as a equation of motion in a state space form. But what I said, I wanted actually like everything in the form of what you call integrable form, that we will see in the dynamic simulation. Right now we will move. So this one you can see what this equation is in the form. So this equation with respect to what you call body frame, right? But what I wanted everything in the inertial frame, so that I no need to actually like make this what you call body frame as an instant, and I cannot actually like explain what are those things. But in the other way around, the body frame equation would be benefit, because your what you call wheels are connected with the body. So whatever you are going to give as a wheel inputs, those would be beneficial directly if you are write the equation with respect to body frame. That is why in the mobile robot community, what we used to do, we will write the kinematic equation, which is actually like eta dot in the form of j of psi into zeta, but the zeta dot we will write in terms of only body frame. So what that means? So we will actually like rewrite this. So what we will do? So we will actually like first take what principle it is. For example, now I call this is actually like with respect to body, and this is what I call with respect to I. Okay. So now if the body is actually like connected with a wheel, and it is actually like start getting a motion. So now what would be the power? So something, right? So I am writing that is the power. But if I realize the same power in the inertial frame, do you think that the power would get changed? No, right? Because only thing you are representing with respect to one frame to another frame. So in the same, the total power you can say consumed by the system will not get changed. So that is what we are trying to use. As long we assume that there are no losses, then what we can bring the principle of conservation of power. So then what one can actually like write, the power to move the robot at the inertial frame supposed to be equal to power to move the robot what you call at the body frame. So then what you can write what is the power relation. So what you know, the velocity and forces, or you can write the input vector and the what you call velocity vector you know. So in the body frame, what would be the velocity vector? Zeta. So what would be the inertial frame? That is eta dot, right? And what you can write here in the you call input with respect to body frame, that already we have written as tau, right? So now the tau dot of zeta supposed to be equal to what I am writing, tau eta dot eta dot. So what this tau eta, this is actually like the control input, or you call input vector with respect to inertial frame, where this tau is actually like inputs with respect to body frame, that is all. So now you know this is we have written in a what so called dot product. This dot product we can write as actually like inner product, you can rewrite as so tau eta transpose into eta dot. So the other way around, tau transpose into zeta, right? But what you know, zeta and tau, you can say that we know from the what you call dynamic model with respect to body frame, and eta dot to zeta you have already relation. That is what we are trying to use. So you can see like what we are doing, that we are assuming that the tau eta is the vector of applied forces and moments with respect to inertial frame, and tau is actually like vector of applied forces and moments with respect to body frame. I am actually like bringing this equation. So now what I am actually like trying to rewrite in the you can say inner and you can say inner product way. Then what you can write this equation you know. So eta dot as actually like j of psi into zeta. So that is what we are actually like trying to substitute, right? So then what you can see, like this zeta goes away, and what remains, tau eta transpose into j of eta. Okay. So here this j psi I am actually writing as j of eta, because this psi is actually like in the eta form. That is what only change we have made. Okay. So now what one can actually like see, I can rewrite this and take transpose throughout both sides, or you can say take transpose in both sides. What you will get? So you will get rewritten equation. So that is what we are actually like writing. So you can actually like rewrite. So this would be j of eta transpose into tau eta is eta. So you can say tau eta equal to tau. So now you can see what you got it, this relation also you got it. So now what you know, so d zeta dot plus n of zeta is tau, and what else you know, so eta dot as actually like j of eta into zeta. So these two equations I am going to use and bringing the inertial frame form. So that is what we are actually like writing. So this is the mobile robot kinematic relation we have obtained, and that I can rewrite in this way. And similarly what I am writing, so differentiating this with respect to time, what I will get eta double dot. So the eta double dot would be in the form of zeta dot and zeta, and you know zeta dot, right. So what zeta dot? Zeta dot I can write as d inverse of, you can say tau minus n of zeta. I can rewrite with the dynamic equation, right. So that I can actually like do it. Right now I am actually like writing zeta dot in this form. I am going to substitute that in the general equation. So this is also we have obtained. So what that means? So this equation I am taking and I am actually like substituting this here. So that is what we are trying to do. Okay. So now this I will substitute from the eta double dot relation, and this I am substituting with respect to this equation. Okay. So now you can see like I substituted that. So what I get? So I get this is a bigger relation. This bigger relation I can regroup it with only acceleration. So what that would be equivalent? That would be equivalent to a inertia matrix. So that is what I am trying to do. I regroup it only acceleration term, and the remaining all I am putting in another group, okay, which I'll put a other vector. So that is what I did. So in the sense I take this inverse, and then I have actually like regrouped and make it. So now what happened? This is what you call d eta, and this whole what you call n eta. Okay. So now you can see like the entire equation you have written in the what you so called inertial frame. So now if you are actually like trying to control your overall system, you can directly say that these are the inputs. Okay. So in the sense you can give the desired generalized coordinate, desired derivative of generalized coordinate, and you can say desired double derivative of generalized coordinate you can give it. In the sense you can give the vehicle position with respect to inertial frame, velocity and acceleration you can give, then also you can do it, right. So now you can see that the overall system you have written with respect to inertial frame. So this is one side. So now what we wanted actually like see how the vehicle behavior will happen. So in the sense we can do the forward dynamics, and if you have given this way, can I actually like do the inverse dynamics. So for that what one supposed to know? So you should know the dynamic simulation tool. Already I gave a small idea in the, you can say, kinematic simulation, how one can use the Euler method. The same Euler method can be extended here. Okay. So that what we are trying to do in the dynamic simulation. So what we are trying to do? So we are actually like trying to take one of the simplest equation which we have derived. Okay. And this is the kinematic equation and this is the dynamic equation. I will be keeping the dynamic model as it is in the body frame, because I told, right, my wheel forces, or you can say my input forces would be with respect to body. So I will keep it that, so that would be easy. Then I will actually like make another loop which will be doing the eta dot integration. So in the sense what I am trying to do, I am trying to do this with respect to what you call in MATLAB. So now we will move to the MATLAB window, then we can actually like see how that stuff works. Okay. So now I am actually like opening one of the new script. So we will actually like see how that takes place. So you know how actually like we have done in the previous. So we have actually like taken the simple Euler method and we have tried how to actually like simulate both forward differential kinematics and inverse differential kinematics. So now the same thing we will extend to the land based mobile robot, where you would be doing the dynamic simulation. So for that I will actually like write it the same way. So dynamic model of a land based mobile robot. So why I am actually like saying the land based, because we are restricted with only one plane. So the off planar movement we are not discussing. Okay. So now what you have to do, so I am just taking, I will be running so many things. So better I will actually like put the mandatory things. So we will come back. So what we did, so the simulation we have started. So the simulation parameter, I will take it from the previous case. So what we have done, we said delta t we denote as dt, that would be 100 millisecond, okay, which we have written as step size. So I will write it that. So then we write total simulation time as ts. So I can take it any, but right now I am taking 10 second. This is the simulation time. So which are actually like same, but you can see something is going to change. Okay. So then the t also like a time span where it starts from 0 and it increase by the delta t time, or you can say the increment by delta t up to ts. So this is what you are a total time. So in the sense, this is I put time span. But what we have done earlier, so earlier we have done as a initial condition. So that is only first order derivative, but here second order derivative. So then the condition would change. So in the sense, what are the things you have to do? So eta you have to define. So eta naught I am actually like defining. So which is x naught, y naught and psi naught. I am taking that as 0 0 just for my convenience. Okay, but we will change it later on. This is initial position and orientation. Okay, of the vehicle. So then what you can actually like see, so I'll put it zeta. So because this is second order derivative, right? The zeta dot we are trying to integrate. So in the sense zeta naught also I am taking. So which is what you call the input command. So vector of, so I'll write initial you can say vector of input command. So which nothing but the body fixed velocities. But what we are trying to do, we are trying to propagate where eta would be getting propagate up to you call 10th second. So in the sense I am actually like taking the first segment is eta naught, because every loop iterating, so this eta would be increased by 1. So in the sense I am taking this eta naught. Then the zeta also like the same way. So that is also like going to iterate every loop. So I am assuming that this is 0. Okay. So now what we have done, we have taken the initial condition. Now we will go to the vehicle parameters. I will write robot parameters because I always teach vehicle dynamics. So that's why. So robot parameters. So here what are the robot parameters we are supposed to use? You have to use what would be the mass of the vehicle, right? I assume that the mass of the vehicle is 10 kilogram. So mass of the vehicle. Then what we have taken, the inertia of the vehicle, that too like z axis inertia. I am taking just a small one. We will take it original when we are doing in real time. So this is the inertia of the vehicle or inertia of the robot, whatever you can call, because this I assume that vehicle because mobile robot. So is there any other things required? You can actually like open the slide. So where we were talking about what you call the stuff. So I'll just show you. So here you can see, is there anything else is coming? No, right? So but if you look at the CG and the body frame is actually like away, then you have to bring the coordinates of C with respect to B, right? So that also like I will bring it here. So in the sense XBC is actually like 0 I am taking, but I'll bring it that, okay. So in the sense these are actually like what you call, so coordinates. So coordinates of mass center, I'll just put it mass center, okay. So what else required? Then that's all. So we'll actually like move to the what you call system or state propagation. So I am just putting state propagation where I will be starting with a for loop. So you may think that we are doing a second, like we will be solving two derivative, then there may be two for loop. No, because we are actually trying to do in a single instance. So in the sense only one for loop where it start from I equal to 1 to length of what you call t. So but what are the stuff you required? You see like we have written everything as generalized. So where we have written u, so u is actually like what? Zeta of 1, because that is what the case, right? And v is actually like what? Zeta of what you call 2 comma I, the ith instant, that is what you call, and r is what you call zeta of, so 3 comma I, right? So then what else you required? You required XBC you have given, YBC you have given, M we have given, I is given. So then that is straightforward, right? You can actually like recall here. Is there anything else is there? No, right? So I'll just use the what you call this one. So So this matrix form I will actually like use it so that would be easy. So you can see like this is diagonally it will come, and as well as off diagonal you can see it is going to give a symmetricity. So I am just using that. Okay, so what that would be? So the inertia matrix I call D. I'll write that is inertia matrix. So inertia matrix, which is what you call D as a matrix. So that would be, so mass, right? So then 0 and minus YBC into mass, right? So I can actually like cross check, right? So this is what the case. So I'll take this equation and put it here so that it is easy for you to recall what we are trying to write. Okay, so this is what we are doing it. Okay, then the second one is 0 comma mass, then m into xbc into, because we have taken earlier is like that. Okay, then you have actually like minus ybc into mass, then so xbc into mass, then the final one is actually like ICZ, so which we have written IZ, then plus mass into, so xbc squared plus ybc squared. Okay, so although it is not there in our case, but we are actually like taking it that as a general case. So now you can see that the inertia matrix, which is 3 cross 3, we have actually like taken. So now what else required? So you need to have the n vector. So I put n vector as small one, so n vector. So that also like would be having 3 components. So I'll use it here. Okay, that vector is okay. So this is the n vector where you can see there is a Coriolis term and as well you call the radial term is there. So I'll actually like use it that. I hope you are able to see my screen. So which is actually like m into r. So multiply with what you call v plus xbc into r. Okay. So then the second term, which is what you call m into r. So u minus ybc into. So I'll actually like type it faster so that it would be beneficial. So this is xbc multiply with u plus ybc multiply with v. Then you can see this is what the last term, and this is what we have actually like done. So then what else required? So remaining all we need to do it ourselves. So the tau, what you call, that is actually like every instant is going to change. So this is I call other vector. Okay, so this I call input. So the input, okay, so the input vector, what we are going to write, fx, fy and mz, but right now I am taking that is simple, only f axis is having 1 Newton, y axis is not having anything, and z axis also not having anything, just for simulating. Then what you need actually like a Jacobian matrix, because you are going to do 2 things. So I am just taking a Jacobian matrix. Why we are doing 2 things? Because it is a 2 you call second order system, you would be integrating twice. So the first one you are trying to get the zeta, then the zeta you would substitute in the eta dot equation. That's why we are writing the Jacobian matrix. So j eta I can write as, so cos psi, okay, so then minus sin psi, so then 0, then what you call sin psi, then cos psi as 0, then what you call 0 comma 0 comma 1. Okay, so this is what the case. So for that, what one supposed to know? So you should know what is psi. So psi I am writing as, so eta of third element, so that also I have written. Okay, so now we can actually like do the integration. So the first one is actually like I am writing zeta dot at ith instant. Okay, so this would be what, inverse of d multiply with what you call tau of ith instant minus n vector, right? So this is what you would do, zeta dot. So then what you want, zeta of I plus 1 iteration. So that what you call zeta of I plus dt into zeta dot, right. So zeta dot of ith one, right. This is what we have taken as a Euler integration. So till now you can see, right, this is only for a velocity update, but you know, like this is actually like second order system. So we need to actually like do little more. So we'll actually like come back to the other you can say state, which is you call eta. So we are actually like updating that eta with the help of eta. Okay. So then you can see like what usually we does, because the eta dot we write in a zeta form. So where j of eta multiply with zeta. So this is what we usually say that that would be equivalent for a first order system. But if you look at this eta is actually like dependent on not only initial velocity, it is dependent on even initial acceleration. So in the sense we can actually like add one more fact. So which is what we call you can see this fact we can actually like add. What that mean actually, like you can see we are adding the acceleration part. What that means, zeta dot also would be coming. So in the sense I am actually like making it. So zeta dot of I. So now you can see like this is actually like dependent on initial velocity and initial acceleration. So now if we actually like close this, then you can see like this is what the eta of update. In the sense I can actually like write this as state update. Okay, so this is I call velocity update. So only issue is actually like here we are multiplying this j of eta, because this zeta and zeta dot is in the other domain where it is actually like with respect to body, what we call instantaneous velocity and instantaneous acceleration with respect to body frame. But we are looking for the generalized coordinate, which is actually like you call earth fixed. So that is what we are actually like trying to find. So now if we apply this way, then you can see like whatever we have done, we have assumed that the tau as the input, and actually like we have taken j of eta actually like calculated based on the psi, and then we are actually like going ahead with zeta dot, and then zeta we calculated based on the velocity update, then eta. So now we can actually like bring the, you can say the file which we have usually uses for the animation. So that I have already copied here. So you can see like this is the animation part. Now if I give any tau, so in this case I modified to 1 and 0.5, in the sense 1 Newton in x and 0.5 Newton in y, and you can see like I modified just for clarity. I will start with 0 initial condition. So now if you look at here what it is giving, this is f axis force and y axis force. So now the vehicle will you can say drag in the lateral direction in an inclined way, that we can actually like explore by looking the animation. So now you can actually like see the animation. So you can see like the 1 Newton force is acting on the body in the forward, and 0.5 Newton is acting on the y direction. So now the vehicle is actually like moving both longitudinal and lateral, in the sense it is actually like moving in an inclined fashion. So now the same thing you want to actually like explore little more. So what, in the sense I will give some non-zero initial condition. For example, the vehicle state already it is actually like rotated something. So then you can realize what is forward dynamics all about. So these are the system states, will come back. So now I am actually like seeing that instead of you can say the eta naught as 0 in the angular. So I am saying that this is actually like 45 degree. So now if I actually see that what happened, the vehicle itself is actually like orient 45 degree. Now if I actually like push the force in f, you can say fx and fy, you can see like from that 45 degree again it would be inclined, not actually like from 0, that you can realize from this particular simulation. You can see already the vehicle is in 45 degree. Now we are actually like inducing the force in x direction and y direction of the body fixed. So that is what you can realize. So now you can see the vehicle is actually with respect to body, whatever the motion earlier you have seen, that is exists. But since it is the system state from the generalized coordinate is modified. So that is why you are actually like getting, you can see like plus 45 degree added in the vehicle. So similarly you want to see what is the system state, for example body fixed velocity, how it is increased. We do not have any friction, right. So that is why you can see the velocity keep on increasing, and similarly system state also like keep on increasing, and we assume that the psi is actually like 45 degree constant. So that is what you can actually like see. But when you see initially 45, but after that you can see like it is gradually actually like changing small variation, right, but it's supposed to be 45 degree throughout, that you can actually like realize at the end. So now I am actually like looking at the other way around. So what the other way around, I am actually like inducing some friction. So for example, I am assuming that it's a viscous friction. So what that means, so the viscous friction coefficient is known, I assume that that is 0.3, and that is actually like in each and every state there is actually like a direct relation. So in the sense zeta of actually like I, so in the sense BV, right, when we write a second order system, the same way it is equivalent, it's a very close to a damping coefficient. This is damping coefficient and this is the damping overall term, this is a velocity base. So now if I actually like add what happened, the velocity would be getting, you can say, streamline, that you can actually like see. So the same scenario, only thing the velocity would be getting somewhat actually like getting settled. So earlier it was keep on increasing. So now you can see like some kind of saturation you can expect at the end of, you can say, simulation probably. Okay. So now you can see that the system is actually like getting curve, but if I increase the time step, you can actually like see that increasing the time step in the sense span time. So right now it is actually like 10 seconds. If I actually like increase probably 30 and I actually like pass the simulation, I don't want, I just want to plot the, you call all the system states. So you can see like the velocity would be getting a streamline. So still it is not, because the friction is actually like not really actually like sufficient to drag this, because it is actually like 1 Newton and it is a frictionless surface earlier. Now you can see like it is not like a straight line, it is curved. So in order to check that, probably we will increase the time again. So probably I will just give 100 and I will just increase the frictional coefficient probably 0.5, just for, because the mass is here is 10 kg, right. So then 1 Newton is actually like very small. So now you can see like it is getting saturated, right. It's very close to 1 meter per second in V and almost 2 meter per second in you can say U. So this is what we call actually like forward dynamics, where you know the force tau which is actually like known to you, and you deploy your actually like equation of motion and then you can verify. For example, now if I give even the angular torque, so then you will get actually like the angular force also, like in the sense it is getting changed. So now that is what you can actually like realize. So what that means, actually like you can see initially it is 0 velocity in, you can say, angular velocity with respect to body frame, but now it is actually getting approximately 0.2 radian per second. So because of that, what happened, the vehicle is actually like start, you can see rotating. So that's why you can see x and y is actually like making a curvy way. So for example, x is actually like getting increased, after that you can see it's something like a sinusoidal form. So now you can actually like bring the simulation part just to give probably. So you can actually like get an idea how it look like. So I am just bringing the simulation part, then you can see that vehicle is getting actually like increase. So here I scaled down or scaled up according to the vehicle overall coordinate. You can see like it started from 45 degree, but it is keep on increasing. So it is actually like probably getting a certain constant velocity in x and y. So after that you can see it is something like a sinusoidal form. It is making a circular, or you can say very close to a circular form. So these all the cases what we have seen as a forward dynamics. So now you can change your XBC, YBC, you can change your vehicle mass, and you can say the inertia, and then you can actually like play all those things. But this is what we call the forward dynamics. So now in the next lecture we will see how this forward dynamics force, what you call tau, the tau we can write as a gamma into kappa. So that we can bring, and then we can actually like see how that would be beneficial in the simulation side, where you can actually like think about how to optimize your, you can say, mechanical parameter, how to increase your performance, all those things we can understand there. Okay. So now you can see the vehicle is actually like getting into one kind of streamlined way. So with that I am actually like ending this particular lecture, and then we can see you can say next lecture. See you then. Bye.